Hello friends, in this video I'd like to solve the following problem from the Argentinian Mathematical Olympiad 2015, problem number 5. We wish to find all prime numbers p such that p cubed minus 4p plus 9 is a perfect square. This problem is, I would say, pretty classical, but it's somewhat hard for me to give you hints. But I suggest that you check manually what happens at p equals 2, 3 and 5, and then for p which are greater than 5, problem solution will base on the following observations. First of all, if p is a prime number and if p divides the product of a and b, then either p must divide a or p must divide b. The second observation is that if a divides b and if a and b are positive integers, then a must be necessarily less than or equal b. And finally, try to show that n, which is, so let's assume that this number equals n squared, and show that n equals pq plus or minus 3 for some positive integer q, and then found the lower bound for q. So give this problem a try and I will see you in a minute. Okay, so I hope that you've managed to solve it. As I suggested, let's see what happens at 2, 3 and 5 to begin with. For p equals 2, p cubed minus 4p plus 9 equals 9, which is 3 squared. Satisfies conditions. If p equals 3, on the other hand, we have the following. 3 cubed minus 12 plus 9. 27 minus 12 is 15. 15 plus 9 is 24. It is not a square. And for p equals 5, p squared plus p cubed minus 4p plus 9 happens to be equal 114, and this is also not a square. From now on, let's assume that p is greater than or equal 7, because next prime is 7. And let's assume, moreover, let p cubed minus 4 times p be equal 9n squared minus 9 for some positive integer n. Okay. So now let's factorize both sides. We will get p squared minus 4 equals n minus 3n plus 3. And let's notice that the left-hand side is divisible by p. This is divisible by p, which means that the right-hand side must also be divisible by p. But, as we have noticed, p divides the product of two numbers if and only if it divides at least one of these numbers, which in turn means that there is a positive integer q such that n equals p times q plus 3, or in the second case, n equals p times q minus 3. Nice. Okay, and now let's combine these two cases into one. So we know that there is a positive constant q, which is such that n equals pq plus or minus 3. Okay. And what can we do now? Now, let's mark our original condition asterisk. And now let's see what asterisk becomes after putting n equals pq plus or minus 3. So condition asterisk becomes the following. On the left hand side we have p cubed minus 4 times p, and on the right hand side we have n squared minus 9. Okay. And now let's expand it. So we have on the right hand side p squared q squared plus or minus 6pq plus 9 minus 9 disappears. And now let's notice that everything is divisible by p, so we can safely divide by p and we get the following. Okay. And let's do one more thing. Let's put terms with p on the left hand side. And let's put everything without p on the right hand side. We have the following. And now let's notice that the left hand side again it's divisible by p. So it implies that the right hand side must also be divisible by p. And that means that p divides plus or minus 6q plus 4, which is equivalent to saying that p divides plus or minus 2 times 3q minus or plus 2. Okay. But now remember that we are dealing with primes which are greater than or equal 7, which are odd. So p cannot divide plus or minus 2. So it must be the case that p divides 3q minus or plus 2. Why? Because p is odd. Very well. And now, using my second or third hint, I don't remember, let's notice that this number is non-negative. So if p divides this number, since p divides 3q minus or plus 2, it must be the case that p is less than or equal 3q minus or plus 2. So we have two cases, minus or plus, but let's notice that it's necessarily less than 3q plus 2. And that allows us to derive a very useful bound, namely q is greater than or equal p minus 2 cubed. Not cubed by over 3. So let's call this condition triangle. And now, using this bound, I will go back to my condition which I marked asterisk, or maybe to this form which I will mark double asterisk. This has to be satisfied. So let's write it again. Let's write it again in slightly different form. So our condition double asterisk becomes the following: pq squared plus or minus 6q minus p squared plus 4 should be equal to 0. And now my idea, the main idea is, notice that q is greater than or equal p minus 2 over 3. This term, after expressing it in terms of p, this will be cubic in p, and everything else will be quadratic or of less degree. So the idea is that our cubic polynomial on the left-hand side will very soon become strictly greater than 0, and then our equality will fail. So that's the idea, but we need to estimate the left-hand side. So let's take only the left-hand side and let's try to estimate it from below. Well, it's necessarily greater than or equal pq squared. Plus or minus 6q is necessarily greater than or equal 6q minus p squared plus 4. Let's further factor out q from the first two terms, and we have pq plus 6 minus 4 times p cubed p squared plus, not 4, or shouldn't be there, minus p squared plus 4. Okay. And now let's notice the following. Since p is greater than or equal 7, and since q is greater than or equal 1, sorry, my bad, there should be minus here, because plus minus 6 is less than or equal minus 6. Since p is greater than or equal 7 and q is greater than or equal 1, this parenthesis is positive. This is a greater than or equal 0 or greater than 0 because what I said. Okay, and now let's notice that we have quadratic function which is already positive, so it must be increasing. It's increasing, so the bigger the q, the bigger the entire expression. So the smallest possible value will be attained when q will be equal to this quantity. P minus 2 over 3, P minus 2 over 3, minus 6 minus P squared plus 4. Okay, so we have this estimate. And now let's simplify it. This entire expression, I will leave details to you. It's a boring algebra, but it will become 1 over 9 times p cubed minus 13p squared minus 14p plus 72. Okay, as I said, this is what? A cubic polynomial. A cubic polynomial which will very shortly, for not that big arguments, it will already be positive. The only question is, at what p does this polynomial become positive? Well, you can either look at the graph or use differential calculus or something else, whatever. It's not very difficult. I will leave details to you. It can be easily demonstrated that this entire expression is greater than 0 already for p which are greater than or equal 14. Again, I will leave details up to you. The idea is that a cubic polynomial very soon becomes positive and stays positive. So look, if p is greater than or equal 14, we know, let's write it explicitly. Now we know that if p is greater than or equal 14, condition which I marked double asterisk cannot be satisfied. which means that for p greater than or equal 14, no, it's not possible to get a square, in other words. So what we have to do now is to check everything else. We have checked 2, 3, and 5 at the beginning of our reasoning. And now we need to check p which are 7, 11, and 13. Only these 3 primes. And I will maybe write the results. P cubed minus 4 times p plus 9 equals 324, which is 18 squared for p equals 7. This expression also is a square, namely 1296, which is 36 squared for p equals 11. Put it here. I want to fit it in this page. And finally, p cubed minus 4p plus 9 equals 2154, which is not a square if p equals 13, which means that our conditions are satisfied for 7, for 11, and also going back to the start of our reasoning, it was also satisfied for p equals 2. So we have only 3 primes which satisfy our conditions. So p is in the set 2, 7, 11. And that is our answer. P is either 2 or 7 or 11. There are no other options. So if you are preparing for some kind of mathematical Olympiad, remember this trick. Remember that if prime divides 2 numbers, it must divide one of them. That can lead to expressing one variable in terms of this prime number and some quotient. Plug it in our equation, as I did in this step here. Then try to simplify this equation and try to find lower or upper bound on the quotient, on Q, as I did here, which I marked triangle. And then try estimating the expression. These types of expressions, polynomials and so on, they stay negative only for limited number of positive arguments. So, in other words, our condition fails for quite small arguments already. As you have seen already, our condition failed already for p greater than or equal 14. And what is left is to be checked manually by you, by hand or by calculator, or whatever. Okay, so I hope that my video was helpful and that you have learned something new. Thank you for watching, and I will see you next time. Goodbye.